Welcome in your own chemistry class. We are studying here chapter 9 coordination compounds. Okay, we have discussed about the entities in terminologies and types of ligands. Now we will discuss in this video about some important topics like classification of complexes. Okay, what is the effective atomic number, what are chelating ligands, and how we can calculate the oxidation number of a central metal atom. Okay, now we will start the topic types of complexes. Okay, we will discuss here the types of complexes on two bases. Number one is classification on the basis of ligands. On the basis of ligands means ligands are similar or dissimilar. Okay, so according to the ligands, the first type of the complexes is homolaptic complexes. Homo means similar, laptic means coordinately bond, means all the ligands in these compounds are same. See, in there are for some examples K4 Fe6. Now I think you are very well known that here K4 is the simple ion, Fe is the central metal atom, it is the entity, it is the cyanide ligand, its name is cyano, and it is the coordination number of Fe. Okay, clear? Everything should be clear in your mind. Okay, here Cu is the central metal atom, all the four ligands are NS3 means amine, and the simple anion is sulfate. In this CMA, central metal atom is cobalt, the all six ligands are aqua, and the simple anion is chlorine. In this ligand with the central metal atom zinc, all the ligands are carbonyl ligand means carbon monoxide. There is no any anion or cation with this entity. Okay, you can identify that which is the central metal in these complexes, which are the ligands, and what is the coordination number of the central metal atoms. Okay, these all are the homolaptic complexes because all the ligands are same type. Okay, the next one is heterolaptic complexes. Heterolaptic complexes means there are two or more than two types of complexes. See, in this complex Pt is the central metal atom, here Fe is the central metal atom, here Cr is the central metal atom, and here Zn is the central metal atom. Okay, there is two types of ligands, two are amine and two are chlorine means chloro, amine and chloro. Here potassium is the simple cation and it is entity anion. Okay, here two types of ligand, sulfato and carbonyl, it is carbon monoxide. Okay, here it is sodium is the simple cation and it is the complex anion. Here with Fe central metal atom, three types of ligands are present, two are aqua, two are carbonato, and two are iodido. In this entity only entity is present, no cation, no anion with zinc means central metal atom. Four ligands are aqua and two ligands are nitrato. Okay, so see, there are all the ligands are of one type, there are the ligands of two or more than two types. So these are homolaptic complexes and these are heterolaptic complexes. Okay, next the second ionization type or second classification of the complexes on the basis of ionization. Okay, on the ionization basis of ionization, the complexes are of four types. Okay, see. Number one, complexes with complex cation and simple anion. Okay, you can easily identify. See in this example, first is entity and other SO4 in ionization sphere. Ionization sphere is after the entity, so it is anion and it is cation. When it is hydrolyzes, then this cation will be complex and this be simpler anion. Okay, see in this complex also it is the entity first and then ionization sphere. In ionization sphere there is chloride ion, so this entity is positively charged means there is complex cation is present and simple anion is present. Okay, opposite of these, the second complex is with simple cation and complex anion. See in these examples, there is this is the ionization sphere means this is the simple cation and this is the entity means complex anion. Same in Cu is a simple cation is in ionization sphere and this is entity. After the ionization sphere, entity is always negatively charged, so there is 4 potassium simple ions, but it is a complex anion. Here Cu plus 2 a simple cation and it is the complex anion. Okay, third type, when both the ions are of complex type, positive and negative both. See, there are two entities in one complex. First entity will be positively charged and the second one entity will be negatively charged. On hydrolysis, complex cation and complex anion is obtained. See in this example also, this is first entity that will be positively charged, this is the second entity that will be the negatively charged, and complex cation and complex anion both are obtained. Okay, now the last type of the complexes is neutral complexes. Means there is entities present but there is no any ionization sphere, so there is no ionization sphere, so they don't ionize. Okay, see in this example, when we dissolve it in water, there will be no any ionization, we will get no any ion, no pt, no ammonia, no chloride, no any ion is obtained because there is only entity, and which ligands or central metal ions are closed in entity can't be ionized, so these are neutral complexes. Okay, thus complexes are divided in 4 types according to ionization and 2 types on the basis of ligands. Clear? Now the second and very important topic is chelate ligands and chelation. Chelate ligands are the bidentate or polydentate ligands. Okay, when bidentate or polydentate ligands with coordinately bond with same central metal atom, then a heterocyclic ring is obtained. This heterocyclic ring is known as chelate ring. These ligands are known as chelate ligands, and this process to make chelate ring is termed as chelation. What is this? Okay, see some bidentate examples or polydentate example. En means ethylene diamine, OX means oxalato, GLY means glycinato, or EDTA means ethylene diamine tetraacetic acid. Okay, some it very important note that chelation increases the stability of the complex. More chelate rings in the complex, more will be the stability. See some first example of this type is with Fe. Fe is the central metal atom with NH3 2 Cl2 and En. It is the bidentate ligand, so it will make the heterocyclic ring or chelate ring. See the coordination number of Fe is 6. 2 coordinate bonds are made by NH3, 2 coordinate bond with Cl, and 2 coordinate bond by En. The bidentate ligands are shown as this type. Okay, or in open structure, Fe first NH3, second NH3, Cl, Cl, and it is ethylene diamine. Both the nitrogens have lone pair to make a coordinate bond. This is the heterocyclic ring. Heterocyclic ring means there are 2 or more than 2 types of atoms are present in ring. In this ring, one Fe, 2 nitrogens and 2 carbons are present, so it is a heterocyclic ring and known as chelate ring. There is only one chelate ring in this compound. If there will be more chelate rings, then the complex will be more stable. Just like this example. See, there are 3 ENN means ethylene diamine bidentate ligands are attached with 1 Cr. There are 2 ethylene diamines and there is 1 ethylene diamine. Okay, see the structure of these compounds. There are 3 chelate rings in this compound. This is the first. There is 2 En means 2 chelate rings are present. There is 1 En means only 1 chelate ring is present. Here 3 chelate rings means it is the most stable. There is only 1 chelate ring means it is least stable. Okay, clear? As chelating rings decreases, the stability also decreases. Clear? These are the chelating ligand. Almost learned that this is the only property of bidentate or polydentate ligands. Okay. Our next small and very important topic is effective atomic number, that is shown as EAN. What is this? This is the total number of electrons present in the central metal atom of complex compound after bonding with ligands by coordinate bond. Means in any example, just like in K4FeCN6, Fe is the central metal atom. Okay, and this is coordinately bonded with 6 cyano ligands. So after the coordinate bonding, how many electrons are present in Fe? That will be the effective atomic number. To calculate effective atomic number, we have this formula. EAN is equal to AN minus ON plus 2CN. AN means atomic number. For example, here the atomic number of Fe is 26. Okay, minus oxidation number. In this entity, Fe is in +2 oxidation state. For to make +2 oxidation state, Fe has released its 2 electrons. So we have deducted this oxidation number. Okay, +2 Cn. Cn means coordination number. To make one coordinate bond, there will be 2 electrons are used, or to make coordinate bond, If the here the coordination number of Fe is 6, so we will multiply the 6 by 2 because 1 coordinate bond means 2 electrons, 6 coordinate bond means 6 into 2 means 12 electron. So by this formula we can calculate the EAN. If the EAN is equal to the atomic number of any inert gas, that the complex will be more stable. Okay, it is also a factor to calculate, to deduct, to predict the stability of the complex. Okay, see first example, EAN of Fe in K4FeCN6. Okay, Fe atomic number is 26, minus 2 because the oxidation number of Fe is here 2, plus 2 into 6, 26 minus 2 means 24, plus 12 is equal to 36. 36 is the atomic number of krypton. So it's this complex is very stable. Okay, another example is EAN of Fe in K3FeCN6. Here Fe is in plus 3 oxidation state. So we will calculate the EN by 26 minus 3 plus 2 into 6 means 23 plus 12 means 35, means this complex is less stable than K4FeCN6 because here the EN was 36 while here the EN is 35. One more example, EAN of Cu in CuNH3,4SO4. Cu, the atomic number is 29 and here Cu is in plus 2 oxidation state. Okay, so we have to deduct the 2, plus 2 into 4, the coordination number of Cu is 4 here, so 27 plus 8 means 35, means the stability of K3FeCN6 and CuNH3,4,6 is approximately equal. Okay, thus we can calculate the effective atomic number of any central atom in any complex compound. Now there is a question, is how will we calculate the oxidation number in this complexes? I tell you that there is plus 2 oxidation state, there is plus 3 oxidation state. How? So now will we see to calculate the oxidation number of the central metal atom. For this, two important things we have to learn, that the total charge of a complex compound is always 0. Okay, like there the total charge of the compound will be 0. Here also the total charge of the compound will be 0. Okay, na? And that will be the sum of the central metal atom, charge of central metal atom, ligands and simple ions also. Means the 0 will be the sum of oxidation number of Cu, the charge on ligands and simple ions. Same here, the potassium ions, charge of potassium ions, charge of Fe and charge of cyanide ions will be sum. The sum of these all the ligands and CMA and ions will be 0. Okay, see examples. K4FeCN6. In K4FeCN6, 4 potassium ions are present. 4. The charge of potassium is +1. It is an alkali metal, belongs from first group. So the charge of K is +1. Fe ka is just assumed as X plus Cn minus. I have told you the all charges and names of the ligands in the last video, types of ligands. Cyanide is Cn minus. Minus 1 charge on 1 Cn, there is 6 Cn. So minus 1 into 6 is equal to 0. So when we calculate +4 plus X minus 6 is equal to 0, then X will be +2. So the oxidation number of Fe is here +2. In K3FeCN6, now +1 into 3. There is 3 potassiums and +1 is the charge of Fe. X is for Fe. Cn6 yani -1 into 6 is equal to 0. Then +3 plus X minus 6 is equal to 0. Then X will be +3. Okay. So the oxidation number of Fe is here +3. Okay. Next in Cu, NH3 whole 4 SO4. X for Cu, 4 into 0. Ammonia is a neutral ligand. Okay, I have told you first of all. Okay, plus SO4 is negatively charged. Sum of all these will be 0. Means X, this is 0 minus 2 is equal to 0. Then X will be +2. So the oxidation number of Cu here is +2. Okay, PT NH3 whole twice Cl2. In here PT assumed as X plus ammonia 0, ठीक है, into 2 plus 2 into chlorine means Cl minus, means -1 is equal to 0. Okay, then X plus 0 minus 2 is equal to 0. Then X will be equal to +2. The oxidation number of PT is here +2. Okay. See, in these examples, in this Cr En का whole thrice plus 3, x plus 3 into 0 is equal to plus 3 is the charge of the entity. Okay, then x plus 0 is equal to plus 3 means x is equal to plus 3. In this example, En to x for Cr En 2 into 0 plus 2 into minus 1, 2's chloride are present is equal to plus 1 is the charge of the entity. X plus 0 minus 2 is equal to plus 1, then x is equal to plus 3. In this example, Cr x En 0 Cl 4 into minus 1 is equal to minus 1. Minus 1 is the charge of the entity. So x plus 0 minus 4 is equal to minus 1 or x is equal to plus 3. Thus we can calculate the any oxidation number of any compound, any CMA in the complex compound. Clear? In this example, CO assumed as X plus H2O 6. H2 charge of H2O is 0. It is a neutral compound. Plus 3 chlorides means 3 into minus 1 is equal to 0. Then X plus 0 minus 3 is equal to 0. Then X plus 3 means CO is in plus 3 oxidation state. Okay, very important thing is that when only carbonyl ligand is present in any entity, the oxidation number of the CMA will be 0. ठीक है, okay, means in Zn whole CO whole 6 the oxidation of Zn is 0. In NiCO whole 4 the oxidation number of Ni is 0. FeOCO whole 5 the oxidation number of Fe is 0. CrCO whole 6 the oxidation number of Cr is 0. Mn2CO whole 12 the oxidation number of Mn is 0. Okay, clear? When only carbonyl, CO is carbon monoxide, it is known as carbonyl. When only carbonyl ligand is present in any compound, in any entity, the oxidation number of the C and central metal atom will be always 0. Okay, clear? Thank you.